Okay, welcome again. So, in the first lecture in this module, we have introduced the linear systems and we were trying to understand the autonomous linear system where A is independent of T. Autonomous, as I mentioned yesterday, the autonomous system has many advantages and we got the existence of solutions in this form. So, we was trying to study this problem. X dot of t is equal to a x t with x at t naught is equal to x naught, and this have a solution in the form of an exponential representation, and solution have this is a unique solution given by e power t minus t naught a x naught. As I said, it has disadvantages. One is the thing, computation of an exponential of the matrix is generally difficult, and secondly it does not reveal anything about the solution trajectories. So, today this is a scenario. In this scenario we have introduced what is called the linear equivalence, whether the matrix A can be linearly equivalent to another matrix, and this is nothing but the similarity of the transformations. So, when you have A is similar to B via an invertible matrix B, the system corresponding to A, as I call the system 1, can be converted to a system corresponding to B, something like y dot equal to B y t, and if the system B is corresponding to a system corresponding to B is easy to the exponential is easy to compute, then the solutions will change, and this change is only a coordinate change, and the nature of the equilibrium point which we have introduced yesterday will not change. If the equilibrium point is stable, it will be stable for even for the transformed equation. So, what we are will be going to see a detailed analysis of 2 by 2 systems, which is much more simpler. In particular, if we can get the matrix B to be diagonal, so an immediately solution can be written, and this is called the diagonalization of the matrix. But as we know from the linear algebra, not that every matrix can be diagonalized, and that is what we have seen. A particular matrix lambda 1 0 lambda cannot be diagonal. That is a simple one example, because the diagonalization is something like equivalent to the existence of n independent eigenvectors, which may not be available to you. What best we can do is what is called the Jordan decomposition, but this Jordan decomposition in 2 by 2 systems is much more easy, and we will have a complete analysis today. So, in this scenario we are going to introduce what is called a phase plane. We introduce the phase portrait. We will do all this in the form of examples, and we will introduce after that what is called a dynamical system corresponding to this one, dynamical system. These notions we will see through examples and system. We will also the concept of flow and vector field. You see all these notions quickly I will recall, but you will also see these notions in more detail when we study the nonlinear system. So, as I said yesterday, this module is a precursor to the nonlinear system, and that is what more interesting problems you will see, more interesting applications we will be able to see these things. Okay. So, let me start with the example. That is the best way to easy. So, let us look at a very simple example. X dot of t is equal to a of x t with x at, say you can put at any point, in particular you can put at 0 because of the autonomous system. What is A? A I am taking to be a very diagonal matrix of the form 1 0 0 minus 2. So, this is a decoupled system. So, this system is nothing but you have x1 dot t is equal to x1 t, and x2 dot t is equal to x2 dot t is equal to minus 2x2. Now you know how to write the solutions. Either you can directly use this formula because it is a diagonal matrix, so you know how to compute that, or you can solve here. Whatever it is, the solution will look like this. The solution of xt is nothing but it is at the origins, it is 0, we are trying to do it, and hence the solution written as e power at. E power at is nothing but e power t 0 0 e power minus 2t x naught. If you want it in the component wise, you will have x1t. So what if you want to learn this course, you have to work this kind of more and more examples here. So you will have the solutions e power t x naught 1. What is the first component of x naught? X naught has two components. So this is x naught 1 and x2t is equal to e power minus 2t into x naught 2t. Now here is where I want to tell you something. As I say, t is a time which is treated as a parameter, but this motion of x1t, x2t, the x1t, the curve x1t, x2t, if you write it, this is equal to your x of t. This moves in the plane, x1 x2, moves in the x1 x2 plane. You see. So what is happening is that this is, can think it as a motion of a particle in the plane x1 x2, and this plane x1 x2 plane is the phase plane called phase plane associated to the system. You see, and you want to understand as this is the motion of the particle, and x1t, x2t is the parametric representation with the parameter being time in the x1 x2 plane. So you want to see the picture, the trajectories in the x1 x2 plane. You see, you have x1 here, you have x2 here, and then you want to see how the trajectories will move along that. If you look at as you said that A is an invertible matrix in this case, the origin 0, this is the origin 0, 0 is the 0 equal to 0 0 is the equilibrium point, which is a solution. So if any solution starting at the origin will remain there forever. But now look at the trajectories x1t, which I have introduced for this. x1t is equal to e power t x naught 1, and x2t is equal to e power minus 2t x02. And this one, if you look at it, whatever be the x naught 1 or x2, depending on the sign of x naught 1, this will go to plus or minus infinity as t tends to infinity. And on the other hand, irrespective of which coordinate it belongs to, this will go to 0 as t tends to infinity. So here is a situation, wherever be the initial point, the first component will go to one of the component will go to plus or minus infinity, and the other component will go to 0. So we want to plot this graph in the x1 x2. So what you do is that to plot this one, you eliminate this one, eliminate t. That is what you do it. You want a closed representation. If you eliminate here, the best way to eliminate, square x1. So you will go back to that one. So if you square it, x1 square will be e power 2t, but e power minus 2t. So you can put it in the denominator. these are all will be constant, x naught 1 and x naught 2 will be constant. So, you will get basically C by x 2. See. So, this is the closed form of this solution. So, if you plot here, suppose you started a trajectory at this point. If you start that trajectory, so this is the point, nothing but some x naught 1 0. Since the second component is 0, these are all these equations is a decoupled system, x naught 2 will be 0, the trajectory will remain, x 2 component will remain to be 0 all the time. So, the trajectory will be here. So, this will be a trajectory basically. On the other hand, if you start a point here, so this is also a trajectory. Only thing which direction we will move, the direction of the motion is the only important thing you have to see, and the direction will prescribe whether it will go to plus or minus. So, in this particular case, so if you start with a point here, and as x 1 component will go to 0 infinity, the motion will be in this direction. So, if you start from here, the motion from, if you start from here, this will move in this direction. On the other hand, if you look at it here, if you start a trajectory from there, again the trajectory will remain in the x 2 itself, because x 1 will be 0 all the time, but the x 2 part is going to 0. So, the trajectory will move towards here. If you start from here, the trajectory will move here. So, this is at the time t equal to 0 or any other time, and as t, this arrow represents as t tends to infinity all the time. You have to understand this arrow as t. So, if you move from here, it will move along this direction to here, all that equilibrium point, but if you start from here, it moves away from the equilibrium point. Now, let us start from here. So, suppose you take an initial point here, this is your point x naught. So, if you start from there, your trajectory will the graph tells you is something like this kind of thing, it is something like a x 1 square equal to x 2. So, it will, the graph if you plot here, so this is the best example to see, it will plot here your trajectories if you plot, because this equation is defined for not only for t positive, it defined for t negative as well. So, if you start here, your trajectories will be here. So, all your trajectories will plot here. So, if you I have your thing. So, if you have your trajectory, you have your trajectories like this. If you have your thing, you will have your trajectories here. If you plot here, your trajectory, all the trajectories will have. So, only thing is that where is the motion, in which direction this will move. For example, if you start from here, as you know that x 1 coordinate go to infinity and x 2 coordinate will go to 0, as t tends to think it moves along this direction, because this is the one x 2 component is going to 0, x 1 component going to infinity. So, if you start, so it will match with this, it will move in this direction. If you start from here, so this is the part where t tends to greater than 0 part. So, if you move here, it will move in this direction. If you have initial point, it will move. You see, so everything moves away from that. So, it is a thing. So, the phase plane together with all the trajectories is the phase portrait of the system. So, the phase plane together with the trajectories, is called the phase portrait of the system, called the phase portrait of the system, phase portrait. The system. So, this is the phase portrait, phase portrait, it is a portrait. So, this gives you the complete analysis of your trajectory, and such an equilibrium point. So, this equilibrium point, because the trajectory at least one component moves. So, if you start a trajectory anywhere here, it is moving away as t tends to infinity, it moves away, you see, that is what. So, move away from the equilibrium points. Whenever that happens, such things are called unstable. So, this is an unstable equilibrium, it is not stable. So, however close it is, it will eventually move away from that unstable equilibrium point, unstable equilibrium point. And in this particular thing, there are different types of stable and unstable equilibrium, and this is something like a saddle. You see it is sitting something like that. A trajectory is moving, and it is called the saddle point actually. Saddle point. This equilibrium is a saddle point. See, this is the situation about the. So, you have the phase plane where your trajectories are moving in Rn space in n dimension. This phase plane is called the phase space. For R3, the phase space is x1, x2, x3 phase, and R4 is a 4-dimensional phase plane. And so, if you are studying a system in n dimension, and it is you want to see the motion of the trajectories in them, and that is the corresponding phase portrait of the system. Okay. So, with that, so we have another notion called dynamical system. You can also call the given system to be a dynamical system, but we can also give a more thing. Consider the map V from R plus or R, if the solution exists, R plus cross Rn to Rn, given by phi at t and x naught is nothing but x t x naught. Okay. And so, what is your system? X dot t is equal to a x t x. Let us start with 0, does not matter as far as this system is concerned, whether you start with a t naught or start with a t, does not matter. So, this is nothing but the solution at the point time t starting from the point x. So, if you start in Rn R2, so you will have an x naught here, the solution will move along this as thing, and this is nothing but the. So, you can imagine the dynamical system is nothing but the motion of the particle. Once you fix x naught, is nothing but the motion of the particle along a trajectory, and it gives you the position of the trajectory at time t starting from x naught at time 0 for this particular system. X dot t is equal to a x t with x at 0 is equal to t. So, it is a, in fact, it is the motion of the particle. Dynamical system is the motion of the particle in the phase plane, motion of the particle in the phase plane, in the phase plane. That is what you have to understand. Okay. There is another related notion. This gives you a better feeling about this. What is called a flow of the system. Flow of the system. Now, what you do is that we will have a physical motivation for this. You look at fixed t, you consider phi t. Phi t is that namely e power a t, t a, e power t a for this system. This is a mapping from Rn, you can view that this is a mapping from Rn to Rn for any dimension. So, you collect everything. So, this collection is called the flow actually. The collection phi t is equal to e power a t as mapping T a such that for all t in the system we have, as you see, that not only for T r plus you can consider, is called the flow. The flow of the system. What is the flow doing? What is the advantage of the flow here? For example, the main advantage when we look at it, a fluid flow, you can think that a fluid at time t equal to 0 in one position, then you view the fluid as particles, and then for each particle after some time the particle will be at another point. But this does not give you this view of a motion of the particle. If you view just a particle in the fluid flow, every particle will move to some other position at after some time t. But for a layman point of view or a natural point of view, when you look at a flow, we never see the flow as particles are moving, rather we see a collective motion of particles. So, this forces you to understand the motion of just one point. We want to see the motion of that point together with its neighborhood. So, if you start with at x naught, this is a different field x naught, and look at this neighborhood, some neighborhood v, and this is nothing but at the position phi at 0. So, phi at 0 of v is v, that is because t 0 it moves there. Then for each t, for look at all the particle in the neighborhood, and you collectively try to see, this will be moving here and this will be moving here, will be moving something. So, you want to see this motion, and all this will be at the different positions. This may be at a position somewhere here, and you will get a neighborhood. So, this is nothing but your phi t at v. So, if you look at that, not only the point x naught and all the neighborhood, you try to see the how the neighborhood together moves, and that gives you the better feeling of the motion of the particle, and that is actually what you are doing, trying to do that through the flow of the system. You see that a column or a neighborhood of the fluid moves in that direction. Okay. So, that is what the flow gives you, the concept of flow, and flow has some nice advantages like kind of semi group properties and all that, which you may probably learn in some other thing. Phi naught of x is always x. The more important thing is that suppose flow move the from at time flow from x, this is essentially tells you that the flow from x, phi t of x gives you from the position x, it moves to the position t at thing, and then compose it with that phi thing will be the same as phi composition s plus t of x. This is a very important thing. So, you flow moves from one position to another position, and then it moves is the same as flow moving from to other position. And another interesting property, this also has a group structure. In fact, for this particular system, you will have phi t of phi minus t of x is equal to x. In general, many of the flow, if the irreversible systems, you may not get the last property, but for these systems are, so you can also reverse the flow. That is why it exists for all t in R. But in a semi group, when you go to partial differential equations etc., when you try to understand this kind of motions, you may not get a group structure, you may only get a semi group structure. That is anyway not the topic of discussion here. And one more notion which you probably would like to think. So, these are all some geometric way of understanding vector field. So, to understand the thing is not, as you see now, is not only understanding the solution, how to interpret the solution, how to view the solution, all part of the study. Vector field for given x in Rn, Ax is another point in Rn, but in the beginning of our discussion long back in the previous lectures, we said in Rn you can view either the points of Rn as points, or you can view also a point as a vector, just like we have seen. So, either you can view this point x, or you can view that point as a vector here. The advantage of this vector, view this as a vector, I can put this vector with the same length parallel to that. So, you can get that view. So, for example, when you have a fluid flow of a particle, the position of the particle you would like to view it as a particle, but on the other hand the velocity at that point is also a point in Rn, but then it is better to view the velocity is a vector placed at that point. So, when you given a dynamical system x dot is equal to Ax, xt you view it as a position and Ax you view it as a vector. So, that way any matrix A gives a vector field structure in Rn, gives a vector field structure, vector field in Rn. So, what you can saying is that for all the points here x, you have a point here x, you can associate a vector. This is vector is nothing but Ax. If you take another point, you will have another vector. All the points can be associated with vectors. So, want to know for a given dynamical system. So, if you look at it here clearly, what are we trying to associate? We are trying to associate x dot equal to Ax. So, when you are looking for a solution xt to this dynamical system x dot equal to Ax, you are looking for this trajectory Ax, so that x dot is equal to nothing but your tangential vector field. This tangential vector field should be Ax, that is what we are looking at it. So, the vector associated to this point, each point should be each point. So, we are looking at a trajectory, solution associated to that one, you want it, these are all should be your Ax, you see. So, that way a solution, a trajectory xt is a curve xt is a trajectory to the solution. At each point the tangent is given from the vector field. The moment A is given to you, you have a vector field given, vectors are associated with all Rn. So, you are trying to find trajectories in such a way, so that each point on that curve the tangential vector coincides with the vector field given to you. So, the moment you are given a linear system like Ax x dot equal to Ax, you want to plot your vector field in that way. So, for the given example earlier, so if you try to plot your vector field, you can see that the vector field, you already know the trajectory. So, your vector field will be like this. So, if you plot your vector field, it will be something like that. So, if you get all your vector field like this. This is your vector field associated. So, if you plot it here, you see. So, you plot here. So that is a vector field. Let me plot again the vector field. So, if you have your vector field to that example or something like that. This is for the given example. So, it may vary like that. if you plot from here, that is how curves. Okay. Similarly, if you plot here like that, these are this point, this is the vector field. No, these directions have changed. That's not the direction. So the direction is in this direction. So if you plot here, the direction will be like this. If you plot here, this will be the direction. You get each point, you will have the corresponding, this will be here because it is a stable one. See? So this is the vector field. So every system you will have a vector field associated with that. So what I would like those who are learning here as an exercise, plot these things. Exercise, plot the curves and vector fields. Curves and curves means solution trajectory. I mean trajectory, and vector field for the above and other examples, for the above and other examples. Okay. So what we have seen is that when you have the solution trajectories and if you plot all the tangent vectors, you will get your vector field. On the other hand, if the vector field is given, you take any trajectory so that the tangent vector to that curve should be from the vector field. It will be a vector field associated to that, and that curve will be the solution to the system. With these basic notions, we will see more and more examples as we go along. What we have seen is only a saddle point example. Now we are going to see the entire analysis for the 2 by 2 systems, which we will do that. Okay. And so basically we want to do a phase plane analysis of 2-dimensional system. That is what we are going to do now. Phase plane analysis of 2 by 2 systems. So you have some terminologies of phase plane, and you are going to see not only here, even the other module of nonlinear systems. So what are the things? So now we want to recall from the linear algebra, and we want to know if A is 2 by 2, we want to know what are the possible 2 by 2 linear equivalent matrices. Typically this can be classified into 3 different categories. What I am trying to say that the linear algebra tells you that every 2 by 2 matrix is linearly equivalent to one of the 3 categories according to the existence, according to the eigenvalues, whether it is a real eigenvalue and distinct, it is a real eigenvalue but multiple real coinciding eigenvalue, or the eigenvalues are complex. So I am going to write the 3 things, which I will not do it, probably some of them you will learnt in the basics. So that is what we called. So the type 1 we want to call it. Type 1, in this case A will be, let me put a notation, this is for linear equivalence to B1. B1 is of the form lambda 0 0 mu. When I say that this notation means that A linearly equivalent, that is the meaning of this, linearly equivalent, means B1 can be written as P inverse of thing. What is B? That means your B1 is of the form P inverse of AP for some invertible matrix P, for some P. That is the meaning of A. When is this happens? This happens when A has 2 distinct real eigenvalues. If A has 2 distinct eigenvalues lambda mu. That means lambda not equal to mu. This is the type 1 matrix. And what are the matrices of P? In this case is easy. You look for, since there are two distinct eigenvalues, it has two eigenvectors which are independent. Put that eigenvectors as column vectors of P, you get your this thing. So, P also can be constructed by obtaining the eigenvectors corresponding to lambda and mu. Because it is independent, it is invertible. Okay. So, that is a case type 1 situation. So, what is type 2? Type 2, A will be linearly, there are two cases in type 2 also. It can be of this form, lambda 0 0 lambda. There are two cases. So, in type 2 there is a case 1, and this happens if A has a double eigenvalue, double eigenvalue means eigenvalue with multiplicity, algebraic multiplicity 2, double eigenvalue 2. That is the meaning of double eigenvalue, means eigenvalue with algebraic multiplicity 2 with, that is the thing. Now, when it has an eigenvalue, a coinciding eigenvalue, there are two cases. There can be two, still it can have two independent eigenvectors, or it can have only one independent eigenvector. So, that is the problem. When you have two distinct eigenvalues, you have two distinct independent eigenvector. When it is a coinciding eigenvalue, it depending on the matrix. It can have two independent eigenvector, and that refers to as the geometric multiplicity. So, the classification within this comes because of the geometric multiplicity. So, this is the case where it gives you two independent eigenvalues. If it has two independent eigenvalue and still it form a basis, and you have the diagonalizability, and with the two independent eigenvectors, and this will be equivalent to B3. In that case, B3 takes the form and non diagonalizable matrix. The diagonalizability in general is not possible. 0 lambda lambda. Again, double eigenvalue with algebraic multi eigenvalue lambda, but only one independent eigenvector. You see, the whole trouble in diagonalizability is the lack of independent eigenvectors. One independent. That means this is the first case, you have algebraic multiplicity 2, geometric multiplicity 2. In the second case, algebraic multiplicity 2, but the geometric multiplicity is 1, and hence it will give only one column vector for P. The remaining vector one has to construct to find the equivalence. You want to write A is equal to 2, you have to find P all the time. In the other cases, getting P through eigenvectors. So, there is a concept of generalized eigenvector, and that is the kind of the whole linear algebra and the Jordan decomposition theorem. In higher dimension, there will be many complications. Some of the eigenvalues are real, some are complex, some are multiplicity, there are certain things have the independent, certain things are simple eigenvalue. So, all complications happen. So, you have to distinguish all that. That is why you do not get the full diagonalizability, you get block diagonalizability. Okay. And type 3 is the last case, which you know already now, you know, type 3. So, the type 3 this is the case. In this case, A will be linearly equivalent to A minus B, B A, where A has complex eigenvalues, lambda is equal to a plus ib, and the other eigenvalue lambda bar is equal to a minus ib. So, you have two eigenvalues and will be linearly equivalent to a minus b, ba, and this let me call it b4. So, our aim now, so if you want to, and as I said again if you want to understand the linear system x dot equal to ax, especially the nature and the behavior of solutions, it is enough to understand the systems corresponding to b1, b2, b3, b4, and then we can record everything. Therefore, in conclusion, we only need to study the systems y dot equal to b corresponding to each of these 4 bi's, bi of y, where for all I equal to 1, 2, 3, 4, with some initial values, say y at 0 is equal to y naught. Once we know that, we understand the nature, and the corresponding a will have the same nature of that one, and then there will be a coordinate change, which we will see how these things are happening. So, we are going to study this one by one now. So, we are going to do type 1 case now. We start with the type 1. So, in type 1, a will be, let me recall again, will be equivalent to b1 is equal to lambda 0 0 mu. This is the case where a has two, again recalling, a has two distinct eigenvalues, lambda mu not equal to mu and real. Okay. So, we want to understand these things. Now, again we will split into various cases. So, again we are putting the various case, and we are assuming here also determinant of whole analysis right now, determinant of equal to 0. If the determinant of a not equal to 0, lambda and mu cannot be, so the only equilibrium point is the origin, no other, because of the invertibility of a. If one of them is 0 or two of them 0, then there will be many equilibrium points. So, that are all special degenerate cases. We will give one or two examples of degenerate cases later. So, we want to understand the situation where determinant of a not equal to 0. So, in the type 1, we have two classifications. Case 1, this is within type 1, where lambda mu, the product lambda mu less than 0. Okay. So, we will start with the examples, and then you will see what happens thing. So, let us take, we already seen one example. So, a similar example we will try to see. So, example, and then we will see that all will work same way. So, we want to understand the phase portrait. So, we will take lambda is equal to say -1. We already considered such an example, but let me do it in a slightly sign change, how the arrows will change. Earlier we considered a saddle point situation. This is a saddle point situation with 1 and -2. So, it will behave same thing. So, what is the corresponding system? You will have y1 dot is equal to y1. This we already studied. So, there is nothing much to do it, minus y1. y2 dot is equal to 2y2, you see, and you have your solution. I can immediately write my solution. y1t is equal to e power minus t y naught 1 and y2t equal to e power 2t y naught 2. This goes to 0 as t tends to infinity. This will go to plus or minus infinity, depends on the sign of y naught 2. Y naught 2 is positive, go to plus infinity. If y naught 2 is negative, go to minus infinity as t tends to infinity. Eliminate x t, we have done exactly the same thing. Eliminate t, you will get it, you square it, you will get y1 square is equal to some constant with y naught by y naught 1 by y naught 2 constant into y 2. So, this is called the saddle point equilibrium, saddle point, which is an unstable equilibrium. Saddle point equilibrium is always an unstable saddle point equilibrium. So, if you plot your curve here, is an exact thing. If you plot here, so this is a equilibrium point and y1 is always going to 0. So, these things are here, y1 part, this will be here and y2 going to infinity. So, it will be here, it will be here. So, if you plot your curves here now, so this will go to y2 is going to infinity. So, it will be here. So, this is your phase portrait. So, if you plot here, this will be like this, this will be like this. So, you have only certain cases I will draw the entire thing. After that you should plot it accordingly. So, if you look at it, the x axis is called stable subspace, stable subspace, and y axis, and so you will define E as the stable subspace E as set of all elements of the form x0 with x in R, and y axis unstable subspace is called unstable subspace, that is called EU is equal to set of all elements of the 0 y is equal to R, and this will give you, this together will give you your R2 can be decomposed into ES plus. This is a general feature which we will see later. Every R and for a given dynamical system we can classify into stable, unstable, plus one more thing will come node when you go to this thing. For the saddle point this is the case, you can classify thing. You can also plot, now you also know how to plot your thing, how to plot the vector field here. So, this is the phase portrait in this situation by taking lambda equal to -1 and mu equal to 2. What I am going to say tell you is that this from here it is not anything specific about lambda and mu. What you need is a different sign. So, this is the case, this is the case for any lambda mu with lambda mu negative. That is what I am saying. If lambda and mu have opposite signs, this is case 1 within type 1. So, whenever you have two eigenvalues, real eigenvalues distinct, but it will have different sign, you can do this one instead of y1 t power minus t y naught, you will get e power lambda t y naught 1, and y2 t will be e power mu t y naught 2. And then if you eliminate t, you will have an expression of the form some y1 power alpha is equal to c by y2 power. So, the trajectories will be the same, it will be remain the same way, only thing depending on the sign which one is negative, which one is positive, the arrows will change. You will have one directional arrows with lambda negative and mu positive, and the arrows will change if lambda negative and mu positive, and the stable axis, either x axis will be the stable in this case, and in that case y axis will be unstable, or you will have x axis unstable and y axis stable. So, this gave the case for all type 1 with the distinct eigenvalues with a different opposite sign will have this case, and so all these equilibrium points in the situation of lambda mu negative is called the saddle point equilibrium. So, the behavior will be the same as saddle point equilibrium. And one more point I want to remark here before going to the next case. If you make this linear equivalence, so if you have this particular matrix B1 which is came from a linear equivalence A1, I told you this is just a change of coordinate system. So, instead of having this thing corresponding to A, you will have a new coordinate system, something like that. You may have a another coordinate system, need not even be perpendicular, but again this corresponding point origin will still remain, because under linear equivalence there is only one equilibrium point which is the origin, and the origin will still remain because as the equilibrium point in that case, and there will be a coordinate change and your trajectories will still be like that. You see the nature of the trajectories will be like saddle point equilibrium with appropriate arrows. You have to put appropriate arrows, that is all. That will give you depending on the sign and thing. So, or here, and this will be in this direction, you see. So, that is what I said, there is no difference in the nature of the saddle point, nature of the equilibrium point for all the matrices, all coming from B1 or B1 corresponding to the matrix A with lambda mu less than 0 will have the same nature of the solution. So, now go to the type 1 and type 1 again with lambda mu, okay, case 2 with lambda mu positive. You see, that is a case. What we had seen is that with lambda mu negative. Now, within this there are two cases, you see, there are two cases with lambda positive, mu positive, and there is another case with the lambda negative, mu negative. You have to understand both these cases. So, the best way again is to take up the example, it will behave in the same way. So, let us take start with an example. So, this is the case again B1. So, you start with example, then you will see that there is no difference. Example, you take B1 to be of the form, it is all in the case of B1 type 1. So, you take to be 1 0 0 2, you take it, you want the case. So, if you do these things, what will happen? If B1 will have, you can write down your solution, your y1 t will be e power t y naught 1 and y2 t will be e power 2 t into y naught 2. See, in either case this will go to plus or minus infinity, because e power t minus depending on the sign, this will also go to plus infinity. Now, if you eliminate here, your y1 square will be constant into y2. This is something like a parabola, you see. So, you have a parabola thing. So, if you plot this curve here, again look at it here. Let us look at our first the equilibrium point. This is an equilibrium point, this is a decoupled system. So, if you start from here, it will remain in the same axis, it cannot move, because if it is in x axis, your y0 2 will be 0 and y2 t will be 0, and hence it will remain in the x axis. But then y1 t goes to infinity, because y1 t is equal to e power t into y0 1, and so the arrows will move along this direction. If you move from here, it will move away from here. If you start from here, it is the same situation, but both eigenvalues are positive, it will move in this direction. In the saddle point equilibrium, if one axis moves away, the other axis moves towards it, but in this case both moves here. So, if you move here, so it will be something like that. So, it will be like that. What about if you start a point here? If you start a point there, both y1 and y2 goes to infinity, but it moves according to this rule, and that is something like a curve, which is something like a parabola. So, as t tends to infinity, it will move along this direction. and this portion will be the t because the solutions are defined even for the minus infinity. So, it moves along these curves. So, if you start from here, it will again move here, for this is for the t positive side and this is for the t negative side. We are at this point is your y naught at t equal to 0, y naught at t equal to 0, you see. This is for the part t negative. So, if you from here if you move again it will move along the parabola, this is the region. So, if you start from here it will move. The parabola may change it. Okay. What I am trying to see that this is the same situation for any lambda mu positive, same case for any lambda positive, only thing is that e power t you will have e power lambda t y naught 1, y 2 t will be e power mu t y naught 1. So, you may not get a relation y 1 square is equal to c y 2, but you get a relation something like y 1 power alpha is equal to c y 2 power beta thing, but the curves may change, the behavior will be same. Such a point is called the equilibrium point, is called a knot. Equilibrium is called, so let me write down this one, knot, NODE, and this is unstable, is called is an unstable knot, because whatever be the solution, any point you start a solution here, solution will move away, however close it is does not matter, it will move. So, of course, the trajectories do not intersect. So, whatever be the close point y naught closer to the origin, the solution will trajectory will think, and this equilibrium is referred to as the knot. Okay. And what I am saying that this is the same situation with any lambda mu, for all lambda positive mu positive, this curve will be the behavior will be the same thing. Now, let us look at this case. So, in this case if you look at it, you start with B 1 in this case, say both with minus 1 0 0 minus 2, you want a system. So, the corresponding system you can write. So, you will have your y 1 t is equal to e power minus t y naught 1, y 2 t is equal to e power minus 2 t y naught 1. So, if you eliminate, you will get again y 1 square is equal to some constant into y 2. The only thing is that this will go to 0, both will go to 0 now in this case. So, if you plot this curve, the curve will be the same. So, you have your equilibrium point. So, in this case if you start from here, only the arrows will change because it is going to 0. If you start here, you will have here, here. So, the curve from if you start here, now this will come towards the origin along that, you see. This is the negative part. So, this is the positive part now. So, if you start from here, so it will here, this is the t positive part. So, this is so if you start anything from here, any point does not matter. If you start from here, it will go to the, it will only go as t tends to infinity. So, it is the same thing, it will go to infinity. So, this is your phase portrait as a, and this is again a situation of a knot. In this case we call a stable knot. You will have this stable knot and you have, and this is same for all lambda mu with lambda mu. Yeah. Okay. So, yeah. So, what we have done is that in the type 1, when it has two distinct eigenvalues, lambda mu negative, you have a saddle point equilibrium which is unstable, one trajectory go to 0, one trajectory go to infinity or minus infinity. when it is lambda mu positive, either both trajectories will move away from the equilibrium point going to infinity, giving an unstable equilibrium. On the other hand, when lambda mu positive with both lambda and mu are negative, both eigenvalues are negative, then the solution trajectory will go to, in fact it goes to the origin in an asymptotic way, giving a stable equilibrium. And we refer to this case with lambda mu positive is a equilibrium point is called a node, and your subspace in the unstable case the whole R2 is an unstable space, in the stable thing whole R2 is a stable case. Now in the next class we will continue with this for the other two cases of type 2 and type 3. What you are going to see is that type 2 more or less behaves like in this fashion with a slight change in the shape of the trajectory, but the behavior will be like a node behavior. But a type 3 case where the eigenvalues are complex, you will have a different behavior. You will also see some periodic behavior, which you are going to see anyway in the nonlinear systems more, the periodic trajectories. With this we will end this particular talk. Thank you.